Hey, we're live. How's it going, Cal 2? I got your Exam 2s graded. I'm gonna start lecturing over Exam 3 stuff. I started trying to do this last time, but I had technical problems and then I gave up, so I'm just gonna start from scratch today. Which is, I guess, not helpful if you already watched that other video. I guess I should delete that. Good news is material is way easier than the other material. You don't have to write a bunch of sentences. It's mostly computations, and the computations, there's some formulas to memorize is kind of the hard part, but mostly you're understanding and using formulas, and that makes this stuff a lot easier. There's some integrating involved, but not like the hard integrals that we were doing on Exam 1. After doing Exam 1, everything here should be easy. Let's try it out. The first big idea we have is a parametric curve. There's sort of three ways of expressing a function. I can just write an equation, and the set of all points that satisfy that equation is often a curve in space. I can also express that curve by solving for y as a function of x, or maybe solving for x as a function of y. Here y would be plus or minus the square root of 1 minus x squared, gives the same curve. And both of these accurately give all the points on the circle and no points that aren't on the circle. But thinking about slopes and things, very often we prefer using this thinking about the circle. Like all of trig wasn't based around either of these equations. I mean, we used them, but we express the circle by saying x equals cosine theta and y equals sine theta. We introduced this new parameter theta that lets us capture every point on the circle. And now, instead of giving you a formula for y in terms of x or x in terms of y, we're giving a formula for x and y in terms of a third thing. This does a lot of cool things. These things are expressed as functions, so I can do some calculus tips on this. But because my x and y are independent coordinates, like, this curve is not a function. I'm not going to be able to write y equals f of x and get the whole thing. At the very least, I need two functions with some plus or minus square root or something. But if I just parameterize the curve, instead of thinking of y equals function of x, I'll put y equals y of t and x equals x of t. Typically, this third parameter is time, but there's going to be places where it makes sense to think of it as an angle instead of time. And now I have a way of describing this motion through the plane, or it would be really easy to jump up to three-dimensional space, although we're not going to do that in this class. Yeah, like you can describe curves that aren't functions this way. It goes up to three-dimensional space. Part of the question is, how do we do regular old calculus using this new description of a curve? It's worth noting that there's only one way of writing this as a function. As opposed to these other ones, the parameterization is conveying extra information. Instead of writing cosine theta and sine theta, I could write x equals cosine of t squared and y equals sine of t squared. And this is still describing motion around a circle, but this version is going to move around the circle faster and faster as time goes by. Like the motion speeds up in some way. Like I can match your first time around the circle will take this length of time, and the next time will go faster and faster and faster and faster. And they are still describing the same curve, but the choice of parameterization, the choice of how fast to move along the curve, has room for other stuff. And if I'm trying to think about slopes and areas and the regular calculus things, I want for that extra information from the parameterization not to be a part of it. So that's the thing we're going to think about, is how do we get rid of the dependence on the passage of time t. We're going to start this off by thinking about the graph of a cycloid. A cycloid, cycle is like the Latin root for wheel. The idea of a cycloid is the idea of the motion of a wheel rolling on the line. I'm going to think about that's a terrible circle. Can I draw a good circle? I'm going to think about a circle with radius 1. I'm going to set it down on top of the origin. That's supposed to be going through the origin. Let's go like this. And I'm going to think about the passage of this point as the circle rolls along. If I wanted to build this physically, I could go to the corner of my room and set up a can and stick a marker on my can so that my marker is drawing on the wall. And as I roll the can, what is the line that is drawn by the marker, right? My circle is rolling along, and as it rolls, if it has rolled this far, then I need to measure that distance along the perimeter. That's where the point is now. And now it's rolled even further, and maybe my point is here. As my point moves along, what is the curve that's going to be passed by that? This curve is going to be called a cycloid. Can we come up with an equation for a cycloid? And because I started this lecture saying it's parametric, probably the thing to do is going to be think in terms of some parameterization. So let's imagine the circle has rolled a little bit. I'm going to think about a small positive theta value, or a small positive roll. I guess before that, let's think about some of the big picture stuff. When is that curve going to hit the x-axis again? Well, how far does the circle need to roll to land where it was at the start, with that point at the very bottom again? If I think about the perimeter of a circle, it's 2 pi r, and the circle has a radius of r equals 1. So that total distance is 2 pi. I need to travel a total of 2 pi before the cycloid touches down on the ground again. And then afterwards it'll probably go back up again. And if I stop at pi, then the circle has done a half rotation, and the point will be at the very top of the circle now. So I know a little bit about it. I know that it hits 0, 0, it hits 2 pi 0, it hits pi 1. That's some information. How do I describe all the other points? Let's grab a clean page. I want to start by imagining a small roll. Suppose the circle's rolled only a little bit, because that's easier for me to... Oh, there's my alarm telling me to wake up from my nap. Turn off alarm. Is it off? I think it's off. Okay. The question we want to ask is, after a small roll, I want to think about this new point as a function of theta, right? Theta being the angle that the circle has rotated by. Black. Here we go. Theta. I'm going to think of the motion of the circle as being a function of this angle theta. I'm going to figure out my x-coordinate as a function of theta. I'm going to figure out my y-coordinate as a function of theta. I know enough trig to know there's a sine and a cosine floating around here. Can I work out what these are? I can never do it on the first try. For me, it always helps to draw the regular orientation unit circle. If theta was over here, I know that this distance would be sine theta, and this distance would be cosine theta. And now I need to reflect this circle so that the angle's down here, and this distance will be cosine theta, and this distance will be sine theta, right? Rotate it 90, and then reflect it that way. Yeah, there's the sine, there's the cosine. Cool. So this new point, what are the coordinates of this point? Well, this distance up was 1, because the radius of the circle is 1, and then after that go down by cosine theta. My new y-coordinate is going to be positive 1, negative cosine theta. I drew this for a small value where the cosine is positive. I could draw a couple more doodles and convince myself it also works if cosine goes negative, and it does. How about my x value? The x value is trickier. I need to think about, like, this distance, this arc length, needs to match this x distance is the base x coordinate before I move left by sine theta. You go back to your arc length thing. The arc length is just theta here. It's r theta, and our r is 1. So this distance is theta, goes from 0 to the center of the circle, and then sine theta goes backwards by the, this green segment is sine theta, the opposite direction. So our x-coordinate as a function of theta is going to be theta minus sine theta. And this is the graph of a cycloid. If I wanted to try to imagine this, I could sort of make a table of values. My values are going to have three things going on because I need to think about theta and x of theta and y of theta. I'm probably going to need some more space here. When theta is 0, I get 0 minus 0 equals 0 for my x value. I get y equals 1 minus 1 equals 0 for my x value. That's good. That lines up with what I said. We start at the origin. If we go out to pi, we should be at our x value is pi minus sine pi is 0, is pi. My y value is 1 minus cosine pi is 0, is 1. That's correct. We said at pi our height should be 1 for the first time. What's going on in between? What's happening at pi over 2? Pi over 2 I have pi over 2 minus, what is sine pi over 2? Sine pi over 2 is 1, so I get pi over 2 minus 1 is about 0.5. I think 0.54? I think. 0.57. Pi is 3.14, so half of it is 1.57, subtract the 1.57. Okay, and what's our y value? Our y value is 1 minus pi over 2. 1 minus cosine pi over 2. What is cosine pi over 2? Cosine pi over 2 is 0. Is it? Oh. This is why I'm confused. I screwed this up. Cosine pi is not 0. Cosine pi is negative 1. So that height is 2. Yes, that makes sense. We're not up as high as 1. 1 is the middle of the circle. At pi, we're up at pi over 2. Okay, so what is cosine pi over 2? Cosine pi over 2 is 0. We get 1. We hit a height of 1, not halfway, but at 0.57, which is significantly less than halfway. So, yeah. I can do some points. That's what it means. A bare minimum to be able to graph something is I should be able to get some dots. I know how to get some dots. It's plugging numbers into points. If I wanted to graph this, I got a couple options. Hey, it's worth knowing. If you have a graphing calculator, it has the option to graph stuff parametrically. Where do you go? You go to mode. The fourth line down on mine has, here's how to graph a thing. I say I want to graph something parametrically. And when I hit y equals, it's giving me two different things. What's x1 of t and y1 of t. These are your x functions and your y functions. Let's graph these. Our first one was theta minus sine theta. I got to put that on as t minus sine t. Y value is 1 minus cosine theta, so I can put 1 minus cosine t. If I hit graph, what's it going to do? It's got a legit question to figure out of how many t values is it going to do. If I go to window, that's part of what's going on. It looks like the default is to go from 0 to 2 pi, which makes sense. What's the step? The step is how often to plug in a value. The thing it's doing is not deep, it's just plugging in a lot of dots and putting those dots on the graph, and I think it connects those dots. So this t step is how often should you be spacing out these dots. Instead of going from 0 to 2 pi, let's go from negative 10 to 10 and see even more of the curve. Let's make our, yeah, that's fine as a step. What do we get? There's our ball rolling along, rolling away. Look at it go. Let's change our window. The y values all go from 0 to 2, so we won't miss anything if we shrink that down to here. Let's make this go from -1 to 4. Will show us a complete scale of it. Is that -1 to 4? Did I graph 1 to 4? Oh, I did the wrong thing. I went to go -1 to 4 here. The X scale is how often should they put a tick mark on. What's going on here? Hello? The door keeps opening. I guess I'm not closing it all the way, but it's creeping me out. -1 to 4. Here's a... Show me this. Yeah. Cool. How do I do calculus on this thing? I guess first off, let's talk about the idea of eliminating the parameter. You should know, in theory, it's possible to convert these things from parametric to a regular form of the function. The idea is I want to pick one of these functions and solve for it. Solving the equation x equals theta minus sine theta, like solve for theta, that's probably not doable. So forget that one. We don't have a shot at this one. The y one we probably do have a shot. If I have y equals 1 minus cosine theta and solve for y, yeah, we can do that. I get cosine theta is 1 minus y, so theta is going to be cosine inverse 1 minus y. That'll at least give us some of the solutions. Cosine inverse doesn't give you the entire graph of cosine. Cosine looks like... I'm doing this badly. But cosine inverse is only giving us this part of the graph. We're not going to get everything, but we'll get some of it. And maybe that equation can suggest what else is going on. So then our x becomes x equals theta, cosine inverse 1 minus y, minus sine theta, sine of cosine inverse of 1 minus y. This is something that simplifies. This is the kind of expression that you want to draw a reference triangle for when you do a trig substitution. The idea is theta is some angle whose cosine is 1 minus y. So his adjacent over hypotenuse is 1 minus y over 1. And then we use the Pythagorean theorem for the last one, square root of 1 minus y squared. So sine is opposite over hypotenuse. I get this is cosine inverse 1 minus y minus the square root of 1 minus y squared. So here's a formula for at least a part of the cycloid. The part it's going to give us is the part where cosine inverse exists is from 0 to pi? Yes. 0 to pi. So we said that that would happen from here to here. This apparently satisfies the equation x equals cosine inverse 1 minus y minus square root 1 minus y squared. It's pretty easy to see that, okay, if I wanted to find the slope of the tangent line at one of these points, I can take dx dy, plug in the right y value. That'll give us the dx dy, which is 1 over dy dx, which is 1 over the slope. And that works in the abstract, but this function is already super gross to take derivatives of, whereas the original functions are super easy to take derivatives of. Even when you can eliminate the parameter, there's a good chance that the parametric version of the thing is way nicer than the unparametrized version. So eliminating the parameter is a nice thing to know how to do, but it's often going to give you something grosser than it's worth dealing with. And like we saw a second ago, solving theta minus sine theta equals x for theta is just not doable, so it doesn't take that much work to come up with a problem where you can't eliminate the parameter even if you wanted to. But that's the idea. Eliminating the parameter means solving one of the equations for t, plugging that into the other equation, and somehow getting a formula for y and x that doesn't have that parameter variable t in it. So, how do we think about slopes? Let's find slope. How do I find dy dx in general case if I'm given something parametrically? Think about some point. I can't write this right. Fix some t naught value. So this point will be x naught comma y naught, which is x of that specific t value comma y of that specific t value. And I want to think about, let's move the t value by a little bit. Where is our new point going to be? Let's call that t naught plus h, or t naught plus delta t. So by wiggling my t value just a little bit, I got another point that should be nearby on my curve, assuming these x and y things are continuous, which seems like a bare minimum expectation if I'm hoping to figure out a slope of something. What is that new value? That new point, the coordinates of that point are, let's call that x1 comma y1 is x of t naught plus delta t comma y of t naught plus delta t. I wiggled my t value by a little delta t amount. How do I find this slope? Slope is the rise over the run. So the derivative should be about new y value minus old y value divided by new x value minus old x value. My new y value is y of t naught plus delta t minus y of t naught. My new x value is x of t naught plus delta t minus x of t naught. If I multiply the top and bottom of this by 1 over delta t, I get a big fraction, the top of which is y of t naught plus delta t minus y of t naught over delta t. My bottom is x of t naught plus delta t minus x of t naught over delta t. And both of these go to a derivative. If delta t gets small, which is the thing I think should give me the slope, I get the derivative of y with respect to t over the derivative of x with respect to t. Each of those evaluated at t equals t naught. So that's nice. The idea of the slope, this is one of these places where writing dy dx as a fraction is bad form, but it's useful anyway because it helps the mnemonic devices work out. Dy dx is going to be dy dt over, that's a y here, dx dt. Which, if the fraction's reduced, and the fractions do not reduce, but if they did, you would get dy dx. So, that's cool. It's worth noting that these mnemonic devices don't work out. There will be a version in Cal 3 where dy dx is delta y delta t over delta x delta t, but with a minus sign. So, like, don't get too used to these mnemonics. But when they work out, it's nice. Here's dy dx. Cool. Let's try this out on our curve. Let's pick a couple points. So for the cycloid, what's dy dx at theta equals pi? At theta equals pi over 4. Now let's do pi over 2. At theta equals 0. Well, dy dx is supposed to be dy dt over dx dt equals, what was our formula? The x was theta minus sine theta? X is theta minus sine theta. Y is 1 minus cosine theta. Cool. So dy dt is dy d theta here. Is, what's the derivative of 1 minus cosine theta? It's sine theta. Dx d theta is, what's the derivative of this? It's 1 minus cosine theta. I get a formula for dy dx, and it's easy to plug things in. At theta equals pi, I get dy dx is sine pi over 1 minus cosine pi. Sine pi is 0. 1 minus cosine pi is 1 minus negative 1, is 0 over 2 is 0, which makes sense with my picture. At the top of the curve, which is what's happening at... I don't have a good drawing of it. At theta equals pi, that's supposed to be the top of the curve. When you have a local maximum, your slope should be 0. All seems well in the world. Great. What's happening at theta equals pi over 2? Dy dx is sine pi over 2 over 1 minus cosine pi over 2. What's sine pi over 2? It's 1 over 1 minus what's cosine pi over 2? It's 0. So this is 1. At pi over 2, which is a point we worked out the coordinates of a second ago, that's where we're up halfway, we have a slope of 1. Our m equals 1. That's supposed to be an m here. That seems reasonable. It's increasing. Cool. What's happening at theta equals 0? Dy dx is gonna be sine 0, 0 over 1 minus cosine 0 is, I get 0 over 0. Oh no. This thing is undefined, and it's not even undefined in the way where I automatically know the slope is infinity. 0 over 0 could be anything. When your formula for derivative gives you 0 over 0, there's a good chance the tangent exists anyway, and try taking the limit. If for example, I had a slope of 1, like as I approach this point, I came in at it with slopes that are getting closer and closer to 1. So at this point I have a slope of 1, at this point I have a slope of 1, and this point I have a slope of 1, and I'm approaching this point where the slope is, where our formula for derivative is undefined, and it's undefined in a, what's the word for that? An indeterminate way. It's worth thinking about the limit. That's probably the right interpretation to take. What's the limit as theta goes to 0 of sine theta over 1 minus cosine theta? How would you work that out? Hopefully you've seen this 1 minus cosine theta and said, aha, I know what to do with you. I want to multiply you by your conjugate. 1 plus or minus sine or cosine looks lonely without its brother. You smush those together. On top I have sine theta times 1 plus cosine theta. And on bottom, I FOIL those out, it's a difference of squares. I get 1 minus cosine squared theta. Which, hey, what do you know? That's my old friend sine squared theta. One of these signs cancels with one of those signs. I get the limit as theta goes to 0 of 1 plus cosine theta over sine theta. And this is no longer indeterminate. 1 plus cosine 0 is 2 on top, sine 0 is 0 on bottom. Instead of 0 over 0, we've revealed it to be, it's actually 2 over 0. It's more 0 on bottom than it is on top. Like we canceled one of the zeros on top. And we were left with something that was even more 0 after the canceling on bottom. This limit is plus infinity. Or plus or minus infinity, depending on what's going on. We learned the fact that there's a vertical tangent at 0. Which makes sense with our graph. When we graphed that thing, it sure looked like it was headed straight upwards at that point. It's not as obvious from thinking about like this can rolling. If I think about this point, as the wheel rolls forward, this point is lifting straight upwards is the direction that it's traveling. Yeah, I guess I could imagine that. You roll it just a tiny bit, it has mostly gone upwards. Like the... Yeah, I can buy that. That's how you find slopes. If there's a formula to put a box around that. Write that down. Put a box on it. How about the second derivative? D squared y over dx squared. This formula is way less obvious than the last one. The main thing to keep in... The way to remember this is to think about what we did just a second ago. We just said dy dx is the derivative of y with respect to theta over the derivative of x with respect to theta. I guess the general one would be t. It's just the special cycloid where we're using theta as our t variable. You need to look at this and think about, this didn't just tell us how to take the derivative of y, it told us how to take the derivative of something. To take the derivative with respect to x of y, the thing we wound up doing was taking the derivative with respect to t of y and dividing that by dx dt. Like this is the grown-up way of thinking about what this dy dx mnemonic device is telling us. The derivative with respect to x of y is its derivative with respect to t divided by dx dt. So, to take the derivative of dy dx, I think about plugging that into this formula. The derivative of dy dx is y double prime is the derivative with respect to t of dy dx divided by dx dt. Put a box around that. If you wanted the third or the fourth derivatives, you'd keep doing that. I would need to take this whole mess is the second derivative, take its derivative with respect to t, divide that by dx dt. That would be my formula for the third derivative. I don't think I have any homework problems that ask you to go as far as the third derivative, but like the pattern is sort of easy to see what's going on here. Let's figure out what the second derivative is doing at those points. For, let's see, how much of this do I want to save? Let me save this line. No. Yeah. Let's copy that. So back to our cycloid. What's d squared y over dx squared? So notice we're doing something fishy. You've talked about the second derivative a bunch in your life, and you almost always used y double prime. You didn't like using this goofy Leibniz notation d squared y over dx squared. This y double prime is just a shorthand for f double prime of x, which is not good notation to use because y is not a function of x here. The concept of the second derivative still exists, and it still means geometrically whatever it meant before. If you were looking for the inflection points, you'd be thinking about where does the second derivative equal 0. But this y double prime notation no longer feels safe to use because the function context that made those apostrophes meaningful isn't there anymore. And when it is there, it's y as a function of t or theta, not y as a function of x. So this y double prime, f double prime, suddenly becomes way more suspicious than it has been all of our calculus life. And we see why Leibniz notation got as popular as it did, because it's a thing that makes sense even without that. We just said our formula is the y double prime concept. The second derivative is the derivative with respect to theta of dy dx divided by dx d theta. What's the derivative of dy dx? Well, here's our formula for dy dx. We have this written down. You need this formula written down somewhere to be able to do this. The derivative with respect to theta of dy dx is going to be, how do I take the derivative of that? It's the quotient rule. Derivative of the top times leave the bottom alone, minus leave the top alone. Derivative of the bottom is 0 minus negative sine theta over 1 minus cosine theta squared. What is this? This is cosine theta minus cosine squared theta minus sine squared theta all over 1 minus cosine squared, which I guess I could FOIL out, but I don't see a good reason to. Hey, I know something about cosine squared and sine squared. That makes 1. I get cosine theta minus 1 over 1 minus cosine theta. Oh, hey! Those are the same, but they're off by minus 1. If I factor out that negative 1, the 1 minus cosine theta will cancel. I'm left with negative 1 over 1 minus cosine theta. That simplifies really neatly. But that's not the second derivative. That's just the top of the fraction. I need to divide that by dx d theta. What's dx d theta? Dx d theta is the same thing it was in the last example. It's still 1 minus cosine theta. So I end up with negative 1 over 1 minus cosine theta squared is our formula for d squared y over dx squared. Cool. Let's evaluate that at some points. What's d squared y over dx squared at theta equals pi? What is it at theta equals pi over 2? What is it at theta equals 0? At theta equals pi, cosine pi is negative 1, so I get negative 1 over 2 squared. It's negative 1/4. What is it at pi over 2? It's negative 1 over 1 minus 0 is negative 1. What is it at 0? It's negative 1 over 0 squared is undefined. Well, it should be undefined. The thing I'm trying to take the derivative of is the slope, and we just said the slope is undefined. You can't take the derivative of something that's undefined. This one never even had a chance, and I don't even need to try and think about a limit here. Although, I couldn't if I wanted to, it's already a thing of infinity. So, we can answer some pretty cool questions now. For example, we can approximate the cycloid. Like, the thing I want to ask is, what's a reason for figuring out what is dy dx and what is d squared y dx squared? And one good reason to figure those things out is the stuff we just did about Taylor polynomials. We can come up with a Taylor polynomial that hugs a curve. If you give me more derivatives, the better polynomial I can get. Well, let's approximate the cycloid by a second order Taylor polynomial at theta equals pi over 2. Theta equals pi. This shouldn't be so tough. How did we do this? A second order Taylor polynomial would be y equals the y value plus the derivative x minus the x value plus the second derivative divided by 2 factorial x minus the x value squared. Like, this is what we do for these when we're doing a Taylor polynomial. We used y prime instead of dy dx, and we used y double prime instead of d squared y over dx squared. But we've talked about how we have good reasons to avoid that nomenclature in this context where y is not a function of x. All these things are things we've worked out. At theta equals pi over 2, we've already figured out the y value was 1. The x value was pi over 2 minus 1. dy dx we worked out earlier was 1. d squared y over dx squared I think we just saw was negative 1. Yeah. So we have all the tools to plug this stuff in. We get y equals 1 plus dy dx is 1, x minus pi over 2 minus 1, plus negative 1 over 2 is 2 factorial, x minus pi over 2 plus 1 squared. Allegedly, this curve hugs the cycloid. Let's see if we can actually verify that. Instead of using a graphing calculator, I'm going to go to something a little prettier. I should bookmark Desmos. Desmos is a nice little online grapher. Hey. Do I need to tell it parametric? Create a new... No. Let's see. If I write x equals... let's say t squared. Nope. Comma? Y equals... How do I put a comma? T? Does it know how to do that? It doesn't know how to do that. How do I tell you to be parametric? No. Oh, there's the wrench. Show me. None of these says parametric. Dang, how do I go parametric? Oh, there's one. Man, okay. I need to turn this laptop inside out to get my keyboard to Google parametric Desmos. How do I graph a parametric curve in Desmos? Oh, just wrap it in parentheses, okay. So, parenthesis, I want my x function, y function. If I say cosine t, sine t, is that going to give me a circle? Hey, it did. You need the extra thing of which t values should it plug in. It's going from t equals 0 to 1. If I go from 0 to pi, then it'll do half a circle. 2 pi will give the whole thing. Okay, what was our thing? Our thing was, x was theta minus sine theta, and our y thing was 1 minus cosine theta. Why don't you like that? Do I need to make it t? You can only figure out if it's parametric if I use t's. Yeah, cool. Why don't you like that? 0. Invalid domain max. Oh, you don't like the period there. There we go. Let's go to negative pi to 2 pi. Let's make it 3 pi. So allegedly, we have a polynomial that's supposed to be a really good approximation for that at pi over 2. That polynomial is 1 plus 1 x minus pi over 2 plus 1. This should, with two terms, already be a tangent line. And sure enough, it looks like it's tangent at this spot. The spot where the y value is 1 is the place where the thing was tangent. But I'm supposed to get something even better if I put a minus 1 over 2, that thing squared. X minus pi over 2 plus 1 squared. Oh! So now we've got the thing bending downwards at, I guess, the same, I want to say the same slope or the same angle, but neither of those are right. Those are talking about the first derivative. I could try the word curvature is something better. It's sort of hugging it at the same bendiness in the correct way. Yeah, this is really close to the curve, way closer than the tangent line was. If I zoom in just a little bit, I can't see the difference between them at all, whereas the tangent line bounced off a lot. This one hugs much closer for much longer. It is a very good approximation to that curve at that point. Let's try doing the same thing at theta equals pi. We worked out our y value, it was 2. We worked out our x value, it was pi. We found dy dx, and it was 0. We haven't found d squared y over dx squared. D squared y over dx squared is, we have a formula right here, negative 1 over 1 minus cosine theta squared. So this is negative 1 over 1 minus cosine pi is negative 1 squared is negative 1/4. Did we already work that out? Yeah, we worked that out on the last page. I remember that now. Okay, so this is negative 1/4. So this one will give me the curve y equals y value is 2. Plus the slope times something, x minus the x value is pi, plus the second derivative, negative 1/4, x minus pi squared. Oh, gotta divide by 2 factorial. So it'll be negative 1/8 is the correct thing to stick in there. Let's try graphing this thing and see if it hugs the curve in the same way. Y equals 2 is automatically a tangent line. It doesn't want to graph a number. Fair enough. 2 minus 1/8 of x minus pi squared. What? Oh, I was not looking at the right curve. I was following the purple one. Let's blank that one. Hey, look! I get a parabola, and it hugs the thing pretty well. If I change u to a 0, I see that's what the tangent line looks like. At 1, I get something better than the tangent line. It's bending in the correct direction also. It's hugging the curve even closer. And if I added a couple more terms, it would presumably be even closer, possibly up to some radius of convergence, after which it stops being so great. Cool. So there's slopes and derivatives using parametric curves. Cool. What else can we do? Oh, here's a good question. How do I find the area of under the curve? That's a thing that we learned how to do in calculus. We should be able to do that with these guys too. I'm turning my computer around again for good writing. Rotate. There we go. Is my stream still working? I'm a little worried that turning my computer inside out seems to not be breaking the stream. That's good. Right, area under the curve. How do you find the area under the curve? Well, the area between the curve and the x-axis is what we would call the integral of the function. That idea is not going to make sense because y is not a function of x. Instead, I'm going to think about how our curve is being the integral of y dx. Y is a thing that I have something I can put in for. My y can be y of t, but I don't know how to integrate that with respect to t. How do I change my dx? This works a lot like it does for substitutions. Dx I can represent by taking dx dt and multiplying that by dt. The general case for if you're doing a region like this would be you have two y functions, a top function and a bottom function. So it would be the integral from the left point to the right point of the top function minus the bottom function, dx. So this is the traditional way of figuring out the area between two curves or something. The same idea will work here. One of the big mysteries is what do you do with the bounds of integration? And that's mostly a thing you need to figure out. If you want to go from a point to a point, you need to figure out what are the t values that correspond with that. You should also think about, is dx dt positive? If your dx dt goes negative, then typically the way I would do it is split it up into parts where the x part is positive here and it's negative here and then it's positive here and then it's negative here, and think about what's happening in all those cases. You're going to get either the correct answer or negative the correct answer. If your dx dt is negative, that means you're moving from right to left, which in a traditional integral sense, I guess you see this in Calculus 1, that if you integrate from 2 to 1, you get the opposite of the integral from 1 to 2. You get the area, but it counts as negative. The same deal here. If your dx is negative, now you're integrating a negative number will give you a negative answer. But I think the best practice is split it into pieces where dx dt is positive or negative, and make sure you understand what those regions are. Very often, you can just integrate from the start to the end, and you'll get the right thing, and the things cancel out in the way that you want them to. But you should do that in chunks, and we'll do an example like that before too long. Here we have a simple one, where if I think about, what was our formula? Our formula was x equals theta minus sine theta, y equals 1 minus cosine theta. If I want the area from here to here, this point is t equals 0, and this point is t equals 2 pi. We've worked that out before. We would expect, like the simplest guess would be we should integrate from t equals 0 to t equals 2 pi. Keep in mind that this is an integral dt, so these are t values. If I just write 0 and 2 pi, that means I'm thinking t equals 0 to t equals 2 pi. It also happens to be x equals 0 and x equals 2 pi. But that's just a coincidence in this problem. Or maybe coincidence isn't the right word for it. And what's the thing I want to integrate? I want to integrate y. Y is 1 minus cosine theta. That is always going to be positive. That's good to check out. And what's my dx? Dx dt is going to be 1 minus cosine t, or 1 minus cosine theta. This should be d theta. These t's are all thetas in this problem. 1 minus k sine theta is always positive. So I don't have anything hinky going on about area canceling area. My thing is always positive. Everything makes sense. This should just be it. What's the integral from 0 to 2 pi of 1 minus cosine squared theta? Or 1 minus cosine theta quantity squared. I guess we need to FOIL that out. We're going to have a cosine squared to deal with. How do you integrate cosine squared? Cosine squared theta is 1 minus 2 cosine theta. It's plus 1 plus cosine 2 theta over 2. 1 plus a half is 3 halves. I'm just doing an integral now. There's not really anything interesting going on anymore. Okay, now we're ready to actually do the integral. Integral of 3 halves is 3 halves theta. Integral of 2 cosine theta is 2 sine theta. Integral of cosine 2 theta is sine 2 theta divided by 2. Evaluate all this from 0 to 2 pi. Plug in 2 pi, you get 3 pi. Minus 0 plus 0. Minus, now plug in 0, get 0 minus 0 plus 0. The answer is 3 pi. Total area of the thing's 3 pi. Does that make sense? If I think about the curve, it's got a width of 2 pi. It goes up as high as 2. So that rectangle would be 4 pi. To get 3 pi, we're filling 3/4 of the rectangle. Yeah, that makes sense. We're definitely filling more than half of the rectangle, because we're bigger than the triangle that goes up to there is half the rectangle. So, cool. This is a sensible answer. Neat. Not too bad of an example. Dum, dum, dum. I think, I thought, man. Crud, I don't have another example in these notes. I'm going to come back and do another example of this next time, where the things go positive and negative and things get a little weirder, but I don't have one like that for this time. Let me move on to the next topic that my notes cover, and I'll come back and do another area one. Area has some weird things that can happen that I should show you. Let's do a simpler question. How do you find arc length? I don't know if you cover this in Cal 1 at your school. I think most of the time arc length is a thing they save for Cal 2. But it's sort of one of these basic Cal 1 type questions. If I graph y equals x squared from 0 to 1, a reasonable question to ask is, how do I find what's the length of this segment? What's the length of that curve? Like if what does that even mean? I guess a thing I should have said at some point is that this is standard y equals y of x format. We can always make it parametric. By introducing a parameter. And you can always, for free, introduce the parameter, let x equals t, then y will become x squared. Y equals x squared becomes y equals t squared. You can do things more complicated than t. You could make x equal e to the t and y equals e to the t squared. You could make x equals cosine theta, then y equals cosine squared theta. You can do whatever you want. This is the simple one. You should note that e to the t is always positive, so if I did x equals e to the t, y equals e to the t squared, then I'm only going to get the positive half, or the half where x is positive, and we're never actually going to equal 0, because e to the x never actually equals 0. You can do goofy junk like that. The default, though, is just x equals t, y equals t squared. So anything that's not parametric can be made parametric for free. If you have x as a function of y, or y as a function of x, just let your input variable be t also, and your other function can stay the same. What would arc length even mean? The best way of trying to understand, like, let's say I didn't know any calculus and I was just trying to estimate the arc length by doing some computation. How would I do that? A typical thing to approximate an arc length would be, we'll take a bunch of little dots, and we will approximate the total length of this curved segment by figuring out what is the length of this, and what is the length of this, and what is the length of this, and add up those lengths. So arc length would be approximately a sum from k equals, 1 to n of, how would I work out that distance? It would be the square root of xk plus 1 minus xk. So if I call this, grab one of these points, this point is xk, yk. Grab the next point, and that's xk plus 1, yk plus 1. The distance between this point and this point is the square root of the difference of the x's squared plus the difference of the y's squared. So difference of the x's squared, difference of the y's squared. I'm using deltas just as an abbreviation for difference of the x's squared, difference of the y's squared. Well, like, I've gotten good at series, but this isn't the kind of thing that I'm good at. My hope is to try and turn this into some kind of integral. How do I turn this into some kind of integral? The trick is going to be, inside that square root, I'm going to divide by a delta t. Like these y values, assuming this curve is parametric, and if it's not parametric, I could make it parametric. We're dealing with parametric curves, so I'm going to write the parametric version of the formula first. This x value and y value are going to be the x value and y value at some t value. I'm going to call that x of tk plus 1 minus x of tk. I'm going to call that y of tk plus 1 minus y of tk. They're both squared. I'm going to divide by tk plus 1 minus tk squared. Divide that by tk plus 1 minus tk, and it's actually squared. To cancel that, I need to multiply by a tk plus 1 minus tk. It was squared, but it was inside the square root. When I pull it outside the square root, I'm left with just this. This, if you think about the mean value theorem, if x is a differentiable function of t, and if y is a differentiable function of t, this thing is going to equal dx dt at some point. This is some point between tk plus 1 and tk. This is going to equal dy dt at some point. It sucks that they're not quite the same point. If they were at the exact same point, this would be an integral right now. Because they're at a different point, you need to do a little bit of work that I'm not going to go through doing. But the work makes it clear that, like, your choice of point in the interval can be this at this place and this at this place, or you think about what's the difference, and the difference goes to 0. This limit turns out to be the integral of the square root of x prime of t squared plus y prime of t squared dt. The fact that our delta tk's got square rooted means the t intervals must be positive. In general, you want to think about integrating from 2 to 1 should be the same as integrating from 1 to 2, but negative. But this thing doesn't make any sense if you let it go negative, so this kind of has formal restrictions that aren't really an issue because you never let those things go negative in practical purposes anyway. Yeah. And if I had a parametric thing where if I just have y equals y of x, this formula, this thing becomes 1 and this thing becomes dy dx. Let's talk about arc length. From t equals a to t equals b, so in a parametric sense, the arc length is the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Non-parametric, if y is a function of x, this becomes, the arc length is the integral from a to b of dx dt is just 1 now, and dy dt becomes dy dx. These are basically two versions of the same formula. It's just when x is t, that becomes 1, and dy dt becomes dx. Let's try it out. Part of the reason they don't show you this formula in Cal 1 is it's the worst. This thing is almost always horrible to try and compute the integral of. Let's try one. Let's just try that arc length of y equals x squared, our simplest, babiest, non-straight line function. From x equals 0 to x equals 1. That'll be the integral from 0 to 1 of 1 plus dy dx squared dx. Our function is y equals x squared. dy dx is 2x. Square that, I get 1 plus 4x squared. How do you do this integral? This looks like it's begging for a trig substitution. What is it? It's sine squared plus cosine squared is 1. Divide both sides by cosine squared. I get tangent squared plus 1 equals secant squared. That's the thing I want to use. I want to let 2x equal tangent theta. So 2 dx is going to be derivative of tangent is secant squared theta, d theta. So dx is going to be 1/2 secant squared theta d theta. This is the square root of 1 plus tangent squared. 1 plus tangent squared is secant squared theta. My bounds of integration need to change. That x equals 0 becomes, what is the theta value where x equals 0? That's going to be theta equals 0. When does x equals 1? It says tangent theta is 2, so theta is tangent inverse of 2. That's not one of the numbers I know tangent of, is it? No, it is not. So I'm integrating from theta equals 0 to tangent inverse 2 of what? It's 1/2 integral from 0 to tangent inverse 2 of secant cubed. Crap, we made a big deal about how secant cubed is a really hard one. We've done that integral. You can do that integral. You can plug in 0 and tangent inverse 2, and that correctly gives you the length of this curve. But just to note how even this very simple function immediately gives a very difficult integral to do. Like it was, even after the trig substitution, it's a hard integral to do. Gross. Let's do one that we know the answer is going to be easy. Let's find the arc length of a circle. The circle is best understood in terms of its famous parameterization, x equals cosine theta, y equals cosine theta. Wait, nope, cosine will not give the correct thing. X equals cosine theta, y equals sine theta. Let's find the circumference of the circle of radius 1. So we want to integrate. This is going to be theta equals 0. If I'm going around the circle once, I'm going to go from theta equals 0 to theta equals 2 pi. So 0 to 2 pi d theta. What's the thing I want to integrate? I want to integrate the square root of dx d theta squared plus dy d theta squared. I got these formulas. What's dx d theta? Derivative of cosine is negative sine theta squared. What's the derivative of y? Y is sine. Derivative of that is cosine theta. The negative goes away when you square it. I get sine squared plus cosine squared. I know sine squared plus cosine squared. That's 1. I'm integrating 1 from 0 to 2 pi. The integral of 1 is theta. Evaluate that from 0 to 2 pi. You get 2 pi minus 0 is 2 pi. The thing we end up integrating is 1, which tells us that at every moment the theta values, the arc length is increasing at the same rate as the angle, which corresponds with what we say about arc length in a pre-cal class, that arc length is just r times theta. Here r is 1, arc length is at all times increasing at a rate of 1 radian per radian. Or 1 radius per radian, I guess. That's why they're called radians, is because they measure the radius. Cool. That's arc length. I want to do one more arc length example that shows off something kind of cool. It's like one of the few examples where the arc length is easy to compute. Let's find the arc length of y equals cosh theta. That's hyperbolic cosine. Y equals cosh x. From, I don't know, let's go x equals 0 to 1. The graph of y equals cosh x is called a catenary. Actually, I'll wait till we've done it to explain this. There's a significance to the shape of this graph. It's a curve you've seen in your life all over the place. I'll show you. Well, let's do this integral. Our formula for cosh is y equals e to the x plus e to the negative x over 2. The thing we want to integrate is from x equals 0 to 1. It's the square root of dy dx squared plus 1 dx. I guess usually we wrote the 1 first, but the plus doesn't care about the order. What's dy dx? Derivative of cosh is sinh. Is e to the x minus e to the negative x over 2. So I want to integrate sinh squared plus 1. If I FOIL out the sinh squared, I get e to the x squared is e to the 2x. That thing squared is e to the negative 2x, and the cross term will be e to the x times e to the negative x will be 1. So I have a minus 1/2 buried inside here as a middle term. When I add 1 to it, that minus 1/2 becomes a plus 1/2. It's not over 2, it's over... Oh, yeah, it's... dang it, I did this wrong. There's 2 cross terms, and it's divided by... The denominator is 2 squared is 4. So it's minus 2/4 is a half. When I add 1, it becomes plus 2/4 is a half. Which, hey, this thing is cosh squared. We mentioned this at the time we first defined cosh and sinh in the first few days of class. The regular Pythagorean identity is sine squared plus cosine squared equals 1. The hyperbolic version of that is cosh squared minus sinh squared equals 1. So when I have that, I missed the h's. Cosh squared minus sinh squared equals 1. So if I move the sinh squared over, this sinh squared plus 1 is becoming a cosh squared. Cosh is positive, the square root of its square is just cosh. The integral of cosh is sinh. I need to evaluate that from 0 to 1. I get sinh of 1, which I can evaluate. It's e minus 1 over e over 2. But there's a special thing going on here, which is that the total arc length from here to here equals the slope of the curve. This graph is called a catenary. A parabola is a thing that if you stretch it or squish it, those are all called those all count as parabolas. The catenary is a little bit more special, that you're only allowed to zoom in and zoom out. If you stretch it horizontally, you also need to stretch it vertically for it to still count as a catenary. And a catenary shows up in nature as it is the graph you get of if you take a rope or a chain or a cable or a string and you let it hang under its own weight, the resulting graph is a catenary, or at least in the abstract. If you had a perfectly, with no air pressure and perfect smoothness to your chain. It's the graph of a rope hanging under its own weight. And you can, if you take a differential equations class, I guess an advanced enough differential equations class will derive why this thing is a catenary. But it's going to come down to the fact that the amount of weight that this link in the chain is holding is the total weight of all this. So something about the amount of stress that it's under causes it to be willing to bend at this much of an angle. This connection is what makes that happen. That's weird. This is one of the important things about cosh, is it gives you this graph that you see between any two telephone lines. Cool. That's everything I want to say about parametric curves, so that's enough for today. Let me take a look at the homework. Do I have the homework open? I gotta log back in. Homework. Zoom out a little bit. Yeah, so you have everything you need to do 138 through 142. Except maybe the area in number 139. I'll come back and do that. I'll do some more area stuff. So yeah, take a look at 138 through 142 in the homework. I should probably add more problems. There's only like one of everything in there. Cool. I'll try and add more problems before tomorrow and post a new version of the homework assignment. It looks like this is the place where I got lazy in typing up the homework last semester. I'm going to stop talking here. That's parametric curves. You can graph them. See ya.